Welcome to another session on the course Integral Transforms and their applications. So, this week we will be looking into the again continuation of Laplace transform, some advanced problems. So, last week I have discussed on um, a problem which I briefly discussed how to solve and asked you to try yourself. So we'll begin with that problem, but now in the context of from the context of application. So like we formulate the problem from its basics, and we'll reach the particular location or situation where uh, we need to take an inverse Laplace transform, which will exactly look like what I have shown last week. Then we'll try to solve that. That's how we proceed today. So if you have any question in between, you can stop me. So um, we'll move to the problem. So am I audible? Okay, good. So the problem here is actually we have to solve for the diffusion equation, which is given here. It's dou u by dou t equal to dou square u by dou y square, which is scaled using variables in such a way that the equation is non-dimensionalized, where the t is a non-dimensionalized time, y is a non-dimensionalized length, and u is the actually it is velocity. So this problem appears in the case of diffusion of momentum. Okay, basically we have a fluid on top of a plate, a fixed plate. On top of that we have a fluid, and there is another plate on the top, and we are impulsively moving this top plate, and the bottom plate is fixed. So the momentum will be diffused from the top plate to the adjacent fluid, and viscosity will diffuse it. So we will get the velocity profile. Initially it will be like this. Then gradually with the time the velocity profile will look like this, and finally it will become something like this, the linear velocity profile. So this vertical distance is measured as y, and horizontal distance is x, but it will not appear in the problem because we assume the flow is fully developed in the x direction, and this is just the velocity profile is plotted with y with the various time, increasing time. So of course the reason for the momentum diffusion is the momentum diffusivity alpha, that is the sorry, not alpha, it's a viscosity nu, kinematic viscosity, and which is absorbed inside the non-dimensionalizers. That's why that is not explicitly appeared in any of this equation. So that's okay. That's just the application part. So now how we solve it to obtain the expression for u of t y. So basically it's a function of two variables, time and displacement y. So we'll take the Laplace transform. That's what we are for that's what objective for today. So we can use Fourier transform also, but Laplace transform will be easier in this situation. So so we have the equation dou u by dou t. So we'll take Laplace transform on both sides of the equation. Okay, so now thing is that Laplace transform we are taking the variable time. So the variable time we to the frequency domain is complex frequencies. Okay, so let's say u is a function of time and y. It's a Laplace transform. We will say it's u cap, which is a function of s and y. Okay, so from the properties of Laplace transform, we know the Laplace transform of a derivative will be s times Laplace transform of the function itself, that is u cap, minus the function evaluated at the location t is equal to 0 at all y. On the right hand side, it is the derivative is in y, so that will not affect. So it's just because of the linearity, we can take it outside, d square by dy square. Then the Laplace transform is going to act on the u inside, so that will be just u cap. Okay, now u of t equal to 0 at all y, that means like at initial time at all the y location, the velocity field which is given as the initial condition, which is 0, so that we apply, so this is actually 0, so we'll get s into u cap is equal to d square u cap by dy square, or d square u cap by dy square minus s into u cap is equal to 0. This is a this is actually not a partial differential equation. Now it is a ordinary differential equation in y. So remember, u is still a function of s and y. Okay, u cap. So now we can solve this. This is actually a second order differential equation with constant coefficients in terms of the variables. If you see, y is actually the variable, and you can see the coefficient is here is s, which is in terms of y it is actually a constant, right? So this we can simply solve, right? We already know the solution of this form. So u cap will be so we can use a characteristic equation for this particular differential equation, and we will find the solution will be for of the type exponentials. So like exponential of root s times y, and exponential of minus root s times y with the particular constants. It's a linear combination of these two, so with the respective constants c1 and c2. And here see, c1 and c2 are general constants. They can be function generally can be constants, or it can in general be function of s. So generally they can be c1 of s or c2 of s. So that dependence that we will be evaluating applying the remaining conditions. So now we want to apply the next boundary condition. Sorry, we have applied the initial condition. Now we want to apply the boundary conditions. So we have two boundary conditions remaining. At y equal to 0, the velocity is 0 always. That means the bottom plate it's fixed. That's why the velocity is 0 always. And at y equal to 1, without loss of generality, we say that the top plate is at location y equal to 1. So where the velocity is a heaviside of time. That means at time equal to 0, its value is 0, but for any finite time, its value is 1. So that means like it's impulsively pulled a plate on top of the fluid. That's why it's given it's a heaviside of time. So we have two conditions here, but they are in actually the time domain, given in the physical time domain, but we want to convert it to the Laplace domain. Then only we can apply that to equation 1. So so if we take the Laplace transform of these two conditions, so u cap for all this at y equal to 0 is the Laplace transform of 0, so that is just a 0. And the another condition is u cap at s at y equal to 1, so that is like the Laplace transform of heaviside of time, and that we know it is 1 by s, right? So that this information we can use here. So but in substituting in equation 1. Okay, so first of all we apply the first condition. So let's say we number this as 2 and 3. So apply 2, we will find that c1 into, let's say 2 in 1 we will get on the left hand side it's 0 is equal to c1 into exponential of 0, that is 1, again c2 into exponential of 0, so that means c2 equal to minus c1. So equation 1 can be now simplified to u cap equal to c1 into e raised to y root s minus c1 into e raised to minus y root s. So which we can write as c1 into e raised to y root s minus e raised to minus y root s. So now I divide this by 2 and multiply with a 2, so that I can write this as 2c1 times this combination here. This particular combination is actually a sine hyperbolic function, right? So I can write it as sine hyperbolic y root s. So this is u cap. Now, if we use the next condition, that is the condition 3 on this particular equation, we have at y equal to 1, the u cap is given as 1 by s. So that means 1 by s is equal to 2c1 times sin h at y equal to 1. So y equal to 1, this is the condition. So from this we can solve for 2c1, which is 1 by s times sin h root s. So this we apply back to this equation, we will finally get u cap. So we solved for all the constants c1 and c2, so we will get it's sin h y root s divided by s times sin h root s. Okay, so this is the equation. This is actually solution, but in Laplace domain. So u cap is the Laplace, the solution in the Laplace domain. So now we want to obtain the actual solution u of t comma y, which is Laplace inverse of u cap. So basically we want to invert this particular form, sin h y root s divided by s into sin h root s. So here in this particular scenario, that y will be a constant and s is the variable, so we have to invert it from s to t variable to that's how we will get the solution. So that we will do, but before that, any doubt in until here? Am I audible?
Yes, sir.
Okay.
Yes, sir.
Yeah. So I hope this is clear.
Yes, sir. Yes, sir.
Okay. So then we'll move on. So this so until here what we have done is that we actually had the differential equation, partial differential equation dou u by dou t is equal to dou square u by dou v square is the general form of the diffusion equation. So this applied to a particular problem where we had two plates, bottom plate and a top plate, with between which there was a fluid which is initially stagnant, and we pulled the top plate impulsively by this boundary condition. So the top plate is at y equal to 1 location. So this equation is scaled accordingly, so that the diffusivity does not appear in the equation. So we just solved it. We are in the final stage. So we took the Laplace transform and solved it. Okay. Now we just need to invert it. That's all. So this particular problem I have given last week also, and I briefly explained how to solve it. And the context I have not given, but this is the context. It appears in the context of a diffusion of momentum, or basically the velocity field of a fluid which is present inside two parallel plates, and the top plate is impulsively pulled. So now so this problem, so usually when we want to invert any Laplace transform, any of that problem, we will look into the tables, and this one don't have any of the form that we know from the table, so we need to actually use the inversion formula. So according to the inversion formula, it's 1 by 2 pi I c minus I infinity to c plus I infinity, then the function sin h y root s divided by s into sin h root s, then e raised to st ds. So this is a formula where c is a real number such that so basically this if we plot the function, and so let me plot the complex plane first. So we have real of s here and imaginary of s. So this is a complex plane of s. In that, so our main function, the entire function that we need to integrate is this, and the integration need to be done through this particular line, which is c minus I infinity to c plus I infinity extending, where this line we have to choose in a way that it lies on the right of all the singularities of this particular function, which is inside the red color region. Okay. So if you see that this function, so we have to find the singularities, but let me tell you, the most singular point, the most right singular point is actually the origin only, 0, and there is no other singular point on the right of 0, so it's okay, you can choose anywhere right of the origin to be the blue line, c minus I infinity to c plus I infinity. And yeah, any question?
Once explain that graph, sir, please. Real and imaginary.
You are not audible. Can you repeat again?
Yes, sir. Now audible, sir. Audible, sir.
Hello?
Yes, audible.
Do you have any question? You raised a hand, I think.
Nothing, sir. Nothing.
Okay. Yeah, so I think
Okay.
that's a mistake then. So, so what I was telling is that the singular point, so there are more singular points for this function that we will see now. So anyway, the blue line is over which we have to take the integral, okay, which is right of all the singular points. So now we will use the method of contour integration by closing the blue curve. So actually the integration need to be performed on this blue line, okay, but we say there is a curve, closed curve like this. So let's say this dashed curve with orientation like this, anti-clockwise orientation. Let's call this curve as C, and the and the line from c minus I infinity to c plus I infinity as L. The both form actually a closed contour. So for a limiting purpose, I will also choose the radius of this circle. I mean, basically this dashed curve, I will choose it have a radius of r. Okay, here also it will go until r and minus r here. So I will say this is CR. It's a circular arc of radius r, capital R, and finally we will take the limit of r tending to infinity. That we will do. So that in this particular situation, the integration is performed from c minus IR to c plus IR. Okay, so what I am saying is that this circle of radius r, this particular contour, plus the line which is c minus IR to c plus IR, this particular line, they together form a closed contour, right? It's a closed contour. So that contour I call let's say gamma. Now from the principles of contour integration, because gamma is a closed contour, right? So the integral over gamma I can write as integral over CR plus integral over the line. Integral of what? This function that is inside the red box, that we will perform. But before that we need to use some results of contour integration. That's why we are doing the splitting first. Okay, so now the thing is that the integral over the line only we need. So we can rewrite integral over line as integral over the closed contour. So remember, because gamma is a closed contour, this is actually a contour integral. So that I putting here also the symbol which has special properties. Then minus the integral over the circular arc of radius r. We need to take the limit of r tending to infinity also, but this is valid irrespective whether r is small or large. Okay, this expression is valid irrespective of whether it is small or large. So let's say this is equation 5 and this is equation 6. Now so we actually need to evaluate this line integral from c minus IR to, so this I can write it is actually c minus IR to c plus IR, which is over the this blue line. Okay, and the contour integral over gamma, which from the principles of contour integration, we let's say any function, for any function, here the variable is s, so I am using s. So let's say small f is a function, any function, we need to do the contour integration over any closed contour, which will be we can always write in terms of 2 pi I times summation of residues of that particular function over all the singularities of the function which is contained within the gamma, contour gamma. Okay, so here we have the function f to be what is inside this red box. So we need to find the singular points of that particular function, then only we can evaluate its residues. Once we find the residues, we will take sum of all the residues, then multiply with the 2 pi I, we will get this contour integral. So that's what we are going to do first. Okay, so first thing is that we need to evaluate the contour integral of the function that is sin h y root s e raised to st by s into sin h root s ds. So this is a function, right? So what are the singular points of this function? So singular points when the denominator is going to 0, the obvious singular points. So now we can see here, from here s equal to 0 is a singular point, and you have to be careful that the function is actually it's a ratio of sine hyperbolic to sine hyperbolic, which also contains s inside. So there can be removable singularities, but that's okay when we find the residues. If it is not actually a singular point or the removable singularity, then the residue will vanish actually at that location. So that's okay. So s equal to 0 is actually a singular point for the function. And now what other singular points it have? So again, another denominator is there, sin h of root s. So sin h root s equal to 0. The solution of this, the solution s of this equation is also expected to be the singular points of the function. So we can always write sin h theta as minus I into sine of I theta. Okay, so in that sense it's minus I into sine of I root s is 0, or in simple form the sine of I root s is 0. Whenever sine of something is 0, the solution is I root s is equal to n pi, right? So this says that root s is equal to minus I n pi, or s is equal to square of that, which is minus n square pi square. So which are basically s equal to minus n square pi square for any n element of integer is singular points. That's what I'm saying. So so finally we got s equal to minus n square pi square. So where n equal to 1, 2, 3, etc. on integers, because s equal to 0 is already we took separately. So the remaining integers only we need to take here. Okay. So they are also singular points. So these are all the singular points, and you can check that there is no other singular points for this particular function, and because there is no other denominator you can put to equate to 0. And also one extra thing that you may think is that there is a square root of s sitting on both the numerator and denominator, and they are special kind of, they can create special kind of singularity, the branch cut singularity, continuous singularity. So you can see this is actually discrete singularities. If I plot them, discrete but infinitely many. S equal to 0 is there, then s equal to minus pi square is there, then minus 4 pi square, minus 9 pi square, like that infinitely many are there. I am not just plotting every one of them, but these are all on the negative real axis. Okay, but they are discrete and points, singular points. They are all poles actually. Their multiplicity, we actually they are of symbol poles actually, we will see that, but they are all discrete singular points. But square root of s can make it complicated, like they can create branch points, but this particular problem don't have that issue, because their square root of s is sitting on both numerator and denominator. So what will happen is that the one sitting on the numerator will create a branch cut, but the one sitting on the denominator will cancel that. So what I'm saying is that on between two of these points there can be a branch cut that one of the square root will create, the other will cancel it, so that on overall we don't see any branch cut across any of these singular points. So there is no branch cuts. You can check this. You can plot the function actually, this particular function which is inside the red box. in the complex plane and check for the discontinuity, and you will see that only poles are there, and there is no branch cut. So that's good news for us. We don't need to worry too much. We just apply the contour integration principles, just 2 pi I times sum of the residues. That's all. If there were actually uh, branch cut, then we need to account for the integration along the branch cuts. Okay, so in that case we can write this as 2 pi I times sum of the residues. So the residue of the function sin h y root s by s into sin h root s times e raised to st at s equal to 0 plus again the residue of the same function, but now at s equal to minus pi square. Then again the residue of the same function at s equal to minus 4 pi square, because it's minus n square pi square. That's how all the residues, all the singular points are distributed. So and so on for infinitely many of such residues. Sorry, singular points. Yeah. So first of all, we start with at s equal to 0. Remember that at s equal to 0 it's a simple pole. So what we have to do is that we just multiply the function with s minus 0 to find the residue. We'll multiply with s minus 0 and take the limit of s tending to 0. So just limit s tending to 0. It's sin h y root s divided by sin h root s into exponential of st. Because multiplied with s, that s is gone. Okay, this s is not there, and we need to take the limit of s tending to 0. The similar thing for the other functions, so other residues also the similar way, because they are also going to be simple poles. So you can check that whether they are simple poles. So if they are simple poles, that for any minus n square pi square, so we will multiply with s minus n square pi square. So minus n square pi square into the function which is sin h y root s exponential of st divided by s times sin h root s limit of s tending to minus n square pi square. But this, now we have n equal to 1 to infinity. We also need to do it. I mean, basically I am saying that these things I am grouping together inside a single summation. So this is what we need to do, like two different limits we need to take, then also an infinite summation. Any doubt until this process? Is this clear?
No sir, clear sir.
Okay, good. So then what we will do is that 2 pi I times the first limit. It's actually easier to do, right? Because it's like you can actually apply what L'Hospital's rule to evaluate this limit, but it's fairly simple. If you think in terms of s tending to 0, the hyperbolic sign will behave like the linear function, like it's like y root s divided by root s into exponential of st is a e raised to st, limit s tending to 0, and you can just cancel them. It will just give y. I guess that is obvious, or you can actually apply L'Hospital rule to obtain that the first limit actually approaches y. So if you have doubts, stop me. I'm assuming that is obvious, that's why I'm skipping that part. Then n equal to 1 to infinity, the summation is there. Now the second limit. So the second limit is also pretty easier to do, but anyway I will go through it through the L'Hospital's rule. So first of all, we need to group them in, accordingly that which part have a 0 by 0 form. So if you see here, this S don't have an issue for any S equal to minus n square pi square, right? Only this part is going to 0. So I will just group that accordingly, like sin h root s in the denominator has an issue, but the 1 by s don't have an issue, and sin h y root s in the numerator will not have an issue, because y is any number between 1 and 0, not going to be equal to 1 or not going to be equal to 0. So in that situation, when s is approaching minus n square pi square, sin h y root s will not going to be 0 or infinity. So that also I can group to place where there is no issue. Similarly, exponential don't have an issue, because that cannot be 0 for any s which is equal to minus n square pi square. But s minus n square pi square, or in simple form it's s plus n square pi square, in the limit of so limit of s tending to minus n square pi square applied to this entire thing, then we will split it into two separate limits. You can see here the one on the right hand side will not have any issue, like it's not by 0 it's not 0 by 0 form or any of that complicated form. We can directly apply s equal to minus n square pi square. But the one on the left hand side, which is actually by 0 by 0 form, where we need to apply the L'Hospital's rule. So that's what we are going to do here. So the left one, we will going to apply the L'Hospital's rules, like we will take the differentiation on the top and bottom, numerator and denominator separately, then apply the limits. So limit is tending to minus n square pi square. On the numerator, the derivative with respect to s, okay, so that is just 1, and the denominator it's derivative of sin h, which will be just cos h root s, times derivative of root s, which is 1 by 2 root s. So that 2 root s will go here. Okay, times this limit we can directly evaluate, which is we just apply s equal to minus n square pi square. So that is sin h so we can apply s equal to minus n square pi square now itself, or probably there is a chance we can combine them together, later apply the minus n square pi square. So I will just keep it that way. So for the moment, it's a sin h y root s exponential of st divided by s. There is no issue there. There is no need of a L'Hospital's rule there. Okay. Now in the left side, if you see here, when s approaches minus n square pi square, now whatever in the left side, this one, don't have any 0 by 0 issues. That also we can directly apply. So now we can directly apply the value of s, which is minus n square pi square, in the limits, both on the left and right. So I guess we can combine them together, because anyway there is a sin h appearing, sin h is there on numerator and cos h on the denominator. We can combine together and write tan h y root s. Okay, so that's a mistake I made there. There's a y setting for the sin h that I didn't notice. Okay, so sin h y root s is there, but cos h don't have y, so it's just cos h root s. But one of the root s we can cancel from the denominator and we can write like this. So we now apply the limit s equal to minus n square pi square. So it will be just sin h y into square root of minus n square pi square into exponential of minus n square pi square t divided by cos h root s, that is root of minus n square pi square times root of minus n square pi square. So if you simplify that, it is 2 into sin h I y n pi. We take the square root of negative 1 as I, then e raised to minus n square pi square t divided by I n pi cos h I n pi. Okay. So now thing is that, as I mentioned earlier, sine of I theta is equal to I sin h theta, cos of I theta is equal to cos h theta. For any theta, this is value. Okay, so that we are going to use here. So you can see here, there's a sin h of I times yn pi sitting there, right? So if you do that, so that means we need the other form, like let's say theta is equal to I phi, then we can write so the same equations I can write in a different form, like sin h of I phi is equal to minus I sin of I theta is minus I phi. So that minus I will take outside, it is like this. Now similarly, cos h of I phi, I can write that as cos of I theta, which is cos of phi. So this is what we are going to use here. So it's 2 divided by I n pi into sin h of I times y n pi. So y n pi, these are all real numbers, I is the imaginary number. So it's that way I can write I into sin of y n pi into exponential of minus n square pi square t divided by this is going to be cos of n pi. And see, this one of the I on numerator and denominator can be cancelled, and cos of n pi I can write minus 1 the whole raised to n, right? So it's 2 into minus 1 the whole raised to n by n pi into sin of y n pi e raised to minus n square pi square t. So this is the residue when the s is equal to minus n square pi square. That is this part. Now we can substitute this particular term here, that is 2 divided by n pi minus 1 the whole raised to n sin of y n pi exponential of minus n square pi square t. Yeah, so that's all. This is the contour integral 1 we started with. This summation, from here onwards, the summation we cannot perform easily, so we will keep it that way. But we have solved the contour integral now. But what we actually wanted is not the contour integral overall, but the line integral alone. For that, we need to subtract from the contour integral the integral over the circular arc. Okay. So before going to that, any doubt in this particular area, how to do the residues and all? So I hope there is no any doubt. So in that case, we will move to how to do the integral over the circular arc. Okay, for this particular function. So now over the circular arc, the function is sin h y root s divided by sin h root s s e raised to st ds. See, the circular arc is on almost like this. So this I can approximate as r e raised to I theta, where theta is going from pi by 2 to minus pi by 2. Or I'll say pi by 2 to 3 pi by 2. Okay. So this that doesn't matter, the angle doesn't matter. I mean, I can say pi by 2 to minus pi by 2 also, but it's better say pi by 2 to 3 pi by 2. Okay, this is the angle theta is moving from, and r is fixed, but we will take the limit of r tending to infinity. So this is about s. S is the variable which is varying. So this we can write as sin h y. Now root s will be root r e raised to I theta over 2 and e raised to t into s, which is r e raised to I theta, which is, I can write cos theta plus I sin theta. Now ds will be r into e raised to I theta, I into d theta, divided by again s, which is r e raised to I theta, sin h root s, which is root r e raised to I theta by 2, where theta is going from pi by 2 to 3 pi by 2. We want this in the limit of r tending to infinity. You can see here this r and this r e raised to I theta we can cancel, and by Jordan's lemma you can show that. So here the so this particular term here, right? So this I can split now into two parts. One of them exponential of t r cos theta, other is exponential of I t r sin theta, and this is just an oscillator integral. This is an exponential integral, and you can see that the cos is negative both in the second and the third quadrant. This is first and this is the fourth quadrant. So you can see cos is negative both in the second and the third quadrant, right? So in the limit of r tending to infinity, and this particular term is exponential of minus infinity always, because cos is negative there, and this integral is going to vanish irrespective of, because the root r here and root r are also going to be explored, but they are having identical nature on the numerator and denominator, so they will balance. But this is an oscillatory nature, this one, sorry. So this is an oscillatory nature, so that does not going to do much things, but the one in the blue color, which is exponential of minus infinity in the limit of r tending to infinity, and in the two quadrants, second and third. So and our integral is over the only those two quadrants, 2 and 3, so that's why it is going to vanish in the limit, and you can show that, so that the integral over CR of that particular function is going to 0. So that means that integral over the line is equal to integral over the contour gamma minus integral over CR, and this we show it is tending to 0. So that means the integral over the line will be equal to integral over the contour. But we so the inverse is just we need to divide by 1 by 2 pi I also. Okay, so from that, so we have integral over gamma here multiplied with this 2 pi I. So if you divide with that 2 pi I, what are appearing inside the red box is the solution for the inverse Laplace transform. So uh, this I have given the expression in the last week's um session. So now I have shown how to approach the entire problem and get the solution. So any doubt in this?
No, sir. Clear, sir.
Okay, so
Okay, sir.
yeah, then that's all for today's session. So we'll meet next week then. Thank you.